What if I told you that we could find a simple, straight line to help predict the future? Now, it might sound like science fiction, but it's actually a 200-year-old idea that powers everything from economics to modern AI. Today, we're explaining linear regression.
I mean, really, this is the fundamental question, isn't it? Whether you're trying to figure out future sales, stock prices, or even something like crop yields, it all starts with one thing: finding the patterns in what's already happened.
So here's our game plan. We're going to start by looking for patterns hidden in a cloud of data points. Then we'll figure out how to draw one single line to make sense of it all. We'll see how that line helps us predict things, cover the crucial rules you have to follow, and finally see how this simple idea became a total cornerstone of AI.
All right, first up, seeking patterns in data. This is really about that universal human quest to find a little bit of order in what often looks like total chaos. It's step one for making sense of pretty much anything. Okay, let's make this real with a simple example. Picture a coffee shop owner. Every day they're tracking two things: the temperature outside and how many cups of coffee they sell. What they really want to know is there a connection here, a relationship between those two things?
So they plot all this data. They put temperature on one axis and coffee sales on the other, and what they get is this. It just looks like a big cloud of dots, right? Each dot is a single day's data. This is what we call a scatter plot, and right now it's just a bunch of noise. Our job is to find the signal hidden inside.
And that brings us to the main event, finding what's called the line of best fit. This is the magic step where we turn that messy cloud of points into a clear, simple trend.
So here's the absolute key. We want to draw one, and only one, straight line that cuts right through that data cloud. The goal is for that line to be as close as possible to all those individual points, on average. This line is basically our best guess at the real relationship happening underneath it all.
And you guessed it, this whole process has a name: linear regression. It's just the formal, statistical method for taking all that data we observed and fitting a straight line, a linear equation to it. That's how we model the relationship between our variables. Now, to do this, we've got to get our variables straight. First, you have the dependent variable. Think of this as the effect. It's the thing we're trying to predict or explain. For us, that's coffee sales. Then you have the independent variable. That's the cause. It's the thing we think is driving the change. Here, that's the temperature. We're basically asking, do coffee sales depend on the temperature? Okay, so we've got our line. We drew it through the data. Now what? I mean, what can we actually do with it? Well, this is where linear regression becomes this incredibly powerful tool, and it really has two main jobs.
First, there's prediction. We can use our line to forecast the future. If the weather report says it's going to be 75 degrees tomorrow, we can just look at our line and make a really solid guess about how many coffees we're going to sell. And second, there's understanding. The model doesn't just say, yeah, these things are connected. It actually quantifies the relationship. It tells us how connected they are.
And here's where it gets really cool. The steepness, or the slope, of our line, statisticians have a fancy name for it, the beta coefficient, gives us a very specific number. It answers the question, for every single degree the temperature goes up, exactly how many more or fewer coffees can we expect to sell? Suddenly, it's not a vague feeling anymore. It's a number. It's a quantifiable relationship.
But let's be real. Life is rarely that simple, right? Of course, coffee sales don't only depend on the temperature. So let's see what happens when things get a little more complicated.
So what we've been looking at so far is called simple linear regression. And this is the math behind it. Don't worry, it's actually pretty simple. Y is our coffee sales, the thing we're predicting. X is the temperature, our cause. A and B are just numbers that define where the line starts and how steep it is. And that little u at the end, that's the error term. It's basically us admitting, hey, our line's not going to be perfect. It's the bit of randomness we can't explain. But this is where the real power comes in. We can start adding more factors. This is called multiple linear regression. So we can add an x2 for, say, the day of the week, because, you know, we all drink more coffee on a Monday, or an x3 for whether there's a big festival happening down the street. Each new factor gets its own slope, its own b, making our model way smarter and our predictions a whole lot more accurate. Okay, time for a super important reality check. Linear regression is an amazing, powerful tool, but it is not a magic crystal ball. It only works if you follow a certain set of rules or assumptions, and if you break them, well, your results can be totally misleading. And here are the four big ones. First, the relationship you're looking at has to actually be a straight line. If it's a big curve, this tool just won't work.
Second, your model's mistakes need to be random and consistent, not following some weird pattern. Third, each of your data points, so each day's sales, needs to be independent. Yesterday's sales shouldn't directly influence today's. And finally, your data should roughly look like a classic bell curve. If you ignore these, you can draw some really wrong conclusions.
So why all the fuss about these rules? Why are they so important? Because, and this is critical, just looking at the numbers from your model can completely trick you. You absolutely positively have to look at the picture.
And this is the perfect illustration of that point. This is called Anscombe's quartet. Now what's wild is that each of these 4 graphs has nearly identical statistics. The same average, the same variance, they even produce the exact same regression line. But when you actually look at them, you see 4 completely different stories. And really, only that first one is a good fit for linear regression. It's the ultimate proof that you have to visualize your data.
Finally, when you run a regression, you'll almost always see 2 key numbers. Think of the p-value as a simple yes or no question. Is the connection between temperature and coffee sales real, or could it just be random chance? A low p-value says, yeah, it's probably real. Then you have r squared. That tells you how much of the change in coffee sales is actually explained by the temperature. A low r squared might mean temperature is a real factor, for sure, but maybe it's just one tiny piece of a much, much bigger puzzle.
So to wrap all this up, let's just zoom out for a second. This whole idea of drawing lines through data, it's not some newfangled thing. In fact, its journey through history is pretty incredible.
Believe it or not, linear regression was developed way back around 1805. 2 mathematicians, Legendre and Gauss, came up with it to predict the orbits of planets 200 years ago. Then, by the 1950s, it had become the absolute workhorse of economics, modeling everything. And today? Well, today it's a foundational piece of modern machine learning, a core algorithm that helps AI systems learn from data.
Just think about that for a second. The exact same core idea that was used to chart the stars is now being used to teach machines, to power recommendation engines, to predict what you're going to type next. At the end of the day, it's all about finding that one simple, powerful line that connects the dots and creates order out of chaos.
So I'll leave you with this question to think about. Now that you see how it works, if you could draw just one line to explain a pattern in your world, anything from your own daily habits to a huge global trend, what would that line connect?